So I think might be the last section that almost identically matches analytical, I think. We'll find out. We never did this in analytical? The sweat story?
We did this, but I don't remember this first page.
Well, it might be a little bit different, but the ideas were there.
Oh, yeah, it was.
So let's see if Alyssa remembers this. The sweat story. That's how I pronounce that guy's name. I don't know if that's right. Remember, what was the story there? Do you remember?
He was doing different types of chlorophyll.
Yeah.
Wasn't he the chalk guy?
Plant chlorophyll. And chalk.
Yeah.
He used chalk as his stationery.
Yeah.
And then he had to get the chlorophyll off the leaves. And
Yeah.
he was wondering about why they changed colors.
Yeah. I mean, isn't that genius? To just, I mean, it seems like that'd be a crazy thing to do. Kind of like it doesn't, I don't know how you relate one to the other, but yeah, to see that those colors are in those leaves and to somehow believe you can separate them out. And that's what he did. You're exactly right. He ended up, I'm sure, different things, right? But this is something must have led from one to the other, right? In figuring all this out. Maybe, that leaf extract was just to have leaf extract in the first place, and then maybe some of it evaporated and you could see different colors in it or something, right? Maybe that could have got him going. And then thought maybe he could separate the stuff out. But anyway, I'm sure he just didn't jump right to it. But you're right, he had ground chalk as a stationary phase. Calcium bicarbonate. Okay, so he used calcium or chalk as a stationary phase, which is very, Brandy? Well, there's one carbon in there, but I wouldn't say organic. Very inorganic, but that's not a choice. So you call it very polar. And it's an odd choice of words, I think, because you look at this compound, it's a neutral. What are they talking about polarity for, Andy?
Well, I guess if it's polar, then it has the ability to bind to other compounds.
Yeah. Well, we have an idea of polar, right? This plus-minus idea, right? Why is calcium carbonate supposed to be thought of as polar? Anybody?
Yeah, oxygen.
Partial charges on the calcium.
It's not even partial. Calcium is a +2. Carbonate is a -2. You take chalk, and is it calcium atom? What's in the? It's supposed to be crystalline. Doesn't look like a crystal. It's supposed to be crystalline compound. What is it composed of? What's in this thing? What holds it together? Go back to the terminology. This is a what type of compound? Ionic. So what holds it together? Ionic bonds. So that means this is composed of what, then, in this little crystalline structure? What's surrounding what? Not molecules. What are they? What are the two things you said? Cations and ions. The cation is the calcium surrounded by the carbonates. Now they could be simple cubic structure, face-centered cubic, body-centered cubic. There's all these other packings, right? But those are the simple ones that we can envision, kind of like just drop a bunch of balls in a bucket, and that's simple cubic packing. So that's what's holding this together. So you can't get, polar isn't even a good word for this. And this is way more than polar. This is full charges here. There should be even more descriptive term for this, but I think English is kind of short on either that or my terminology isn't very good. But this is extreme polarity. Okay. So now whenever this type of stationary phase is used nowadays, that type of chromatography is referred to as normal. All right? There it is, normal. I don't see much normal about it, but they call it normal. Nobody does it anymore. Later in the 60s, LCs came out. Okay. So we're talking about like 50-some years. I don't know why it took so long. But maybe it's the computer controls business. That this liquid chromatograph was there. I mean, all they had to do was apply pressure to it, and technically they have a liquid chromatograph. But I think they're probably talking about you're probably getting more into business end of things here. Of all known organic compounds, only blank percent you can put on the GC. It's 20. Ooh, someone remembers. What percent can you put on the LC? Given the right column, given the right mobile phase, there's no limit. Given the right detector, whatever. Can it be as big of a protein as you want? It doesn't matter. You just have to modify the instrument a little bit. Some differences. I guess there's some differences. That leads into differences between gas chromatography and liquid chromatography. See if you can spit some out. We'll start with Andrew. So maybe just kind of list a characteristic of each or a difference, however you want to do this.
I mean, you're limited to gases and
Yeah, that's a good one. Limited to gases. I guess you could finish that sentence. That do not blank at the inlet temperature. That do not what? Decompose, burn, fall apart, whatever word you want to use. Decay. That's a good one. Randy, what's another one? GC-LC difference. What's that? Yeah. What? Yeah, the mobile phase is the liquid. Guess you know what? Man, we could probably be a little better with this. Mobile phase is a liquid. Gas chromatography, mobile phase is a gas. What would we answer over here as a contrast? It's limited to gases that do not decompose at the inlet temperature. Over here, yeah, there is no inlet temperature, right? I mean, it's not limited. You could say no inlet temp. I guess you could modify it to have an inlet temp if that would help you, but yeah, essentially not limited. What else? Oh, who am I picking on? Mel. Maybe another one. Think about the instruments themselves or how you would actually do the chromatography. I think using a small amount, that might depend on the detector, right? Because if you're talking about an absorption type of detector, some kind of thing that does absorption, then you're kind of not talking about as low of a limits as you are burning something like a flame ionization or something. So GC can be more sensitive, but I can give you this. This is not what you said, though. Higher resolution. All right? It's easier. You get higher resolution.
Isn't the GC like 1,000 times more expensive than the LC? Or
Well, they're both pretty expensive.
Yeah.
Yeah, they're both on the same borderline. Like, if you want to get well, maybe this is about 6 years old, this statement, but LC, liquid chromatography mass spectroscopy, was the big thing. And it is the big thing. And that's like 100 grand. A GCMS has been around much longer, and that's like around 60 to 80 grand. So they're all really expensive. Higher resolution. Which one changes the mobile phase composition? LC. Which one has how is the stationary phase different? The GC really has a higher resolution because its stationary phase is how long? Yeah, a big coil. Meters and meters and meters and meters. You can make it as long as you want. So that's a big difference, right? Long stationary phase or something, right? That might be the same idea as saying that one. Okay. But I don't know. I mean, is there any more that are really kind of? Let's see what I wrote in here. I don't know if I even wrote anything. Yeah, I didn't.
I looked it up, and
Mm-hmm.
it says that the LC detects larger molecules because of the liquid and solid, versus the GC detects.
Yep. Okay, that's a
small
good one.
molecules.
So that's a good one. Let's put a number on that. Molar mass. Typically less than so many grams per mole. LC has no limit. Because it has to be volatile. And that's supposed to be a less than symbol. That thing right there. What do you think the number is? Did you Google that? It's 400. From what I read. Maybe you can Google something different. But it's a number up there, around there. If you get bigger than 400 grams per mole, it's not going to be volatile enough for you to, because like someone said, it has to be a gas. Otherwise, you have to heat it up so much, it's just going to fall apart. What else did your Google say?
I just talked about the difference in molecules
Yeah.
as looking at that question.
Okay. LC manufacturers spend a lot of resources to make their liquid chromatographs ultra low volume in order to minimize blank blank. Yeah, they want pretty peaks. They don't want fat peaks. What causes zone broadening? Remember, there's two types of diffusion and things, but in general, you just say zone broadening, you're done. What is the difference between isocratic and gradient elutions? Oh, Andy, what's the difference there? This is an isocratic elution. This is a gradient elution.
With gradient illusions, there would have to be a difference in the way that the stationary phase is set up.
No. Anybody help them out? Think of all these buttons and things you can do, because now these things, everything's going to be computerized. everything can be controlled. You can mess with, on the LC, you can mess with the temperature of your little column. Little because it is little, right? This is a long one. A lot of them are shorter than this. You can mess with the temperature of this. You can mess with the flow rate. You can mess with the composition of the flow rate. So you'll have all these bottles. You can suck out different volumes. You can mess with easy things to mess with. Temperature, flow rate, the amount you inject. You can mess with whether you, so there's, and then you can mess with the auto sampler. There's some parameters there. But I guess what I'm saying is if all these buttons you push, or the setup, right? Once you push start, so the little thing starts going to inject the sample or whatever, nothing changes after that. In other words, there's no parameters that are changing. For example, temperature can't be changing, no matter where the temperature is. The composition of the stationary phase or the mobile phase, nothing can be changing. That's isocratic. And then gradient, oh man, 1 minute into the run, I'm going to change this. 10 minutes into the run, I'm going to make the flow rate go to 5 mils per minute. 18 minutes into the run, I'm going to change the mobile phase composition if it's an LC. So, or I'm changing something from the very beginning. I'm going to ramp in the GC. Once I hit start, that oven is going to start at 40 degrees, and it's going to constantly go up 5 degrees per minute. So you're just changing something during the run. That's gradient. Okay, that's the difference between isocratic and gradient. So here's an example of pretty much what I said, I think. They're talking about, the bottom one is, the temperatures aren't there, but let's just say that's isocratic GC run at 100 degrees Celsius. So when they say that, what's at 100 degrees Celsius? The column, the oven, right? Remember the column's inside an oven. So they're not talking about the inlet or anything. They're talking about the oven, because that's the important part. And then up here, look at the baseline. See how it's coming up? So you can tell, man, this is getting hot as time progresses. So this is definitely a gradient run. Gradient. A GC gradient run. It might be start. Looks like they started at the same temp, because look at that, those look identical. So I'm going to say start at 100 degrees Celsius, and then increase it 25 degrees per minute or something. Something like that. I'm not sure if that's exactly what happened, but it's going to be really similar to something like that. And you can set all that up in the method before you hit start. Some of you already played around with that. So our flow diagram. So I don't know if you've seen the HPLC upstairs, but if you have, that would help you fill in this flow diagram. I think we did this in analytical. Okay. So that means Andrew has all the answers. And let's go around. See if you remember this. Start with Andrew. What were these 4 squares?
These are samples. 1, 2, or A, B, C, D.
Yeah, they're labeled A, B, C, D, but they're not samples. They're solvents, right? You can label them A, B, C, D if you want, but they're solvents. Different solvents. And there's no reason why C has to be pure ethanol. It could be, C could be 80% ethanol, 20% water. right? D could be a 0.2 molar sodium phosphate buffer. Right? These could be any solutions you want. They don't have to be solvents. They could be solutions. Solvents / solutions, I guess. Okay, so each of these is connected, right? Getting sucked out into the blank valve. What did we call this, Brandy? Started with an S. Yeah, starts with an S. Do you want to remember? Mm-mm. There should be some way to get people to remember. It must be like a game or something. Somehow you got to make it important to you. But I mean, it's not that big a deal, right? I mean, so it's not that your life really doesn't depend on it. Solvent proportioning valve.
I think it started with a P, and he said S and I understand.
Yeah. Okay. So something has to be sucking these solvents out. So what's probably next? The pump. And then there's probably a better word for a pump. Like they could have peristaltic pump. They could have binary pump, quaternary pump. But anyway, the pump, right? But the pump is essentially, and you'd think they'd have something better by now, but this works really good, right? The little piston idea. But then you get high pressure, low pressure. So then you get these pressure ripples. So now this is actually optional. Depends on the manufacturer. And if you look at ours, you can see the little pressure ripples. And then when the manufacturer came by, they didn't want to point that out. But you can see them, it's obvious, especially if you zoom up. Because the instrument we bought does not have this. What was it called? Oh, that's coming. Everybody's going to have a guard column to protect their expensive column. It's the kind of like, I don't know, I forget the exact word for it, but the point is to remove, because if going through your detectors, high pressure, low pressure, high pressure, low pressure, right, you're going to have more stuff, less stuff, more stuff, less stuff. So that's going to be your background. That's going to be your baseline. Instead, you want it to look like this. And that's what the pulse dampener does. You can call it the pressure pulse dampener or something, but that's, our instrument doesn't have it. Okay. Now, I already mentioned this is the guard column. So that means what's going to come before the column? What's that? The inlet, your injector or whatever, right? Inlet sounds like 2GC-like. So I'm going to call it an injector because it's a high-pressure system. So you have to physically blast your sample into it. So, but inlet, same idea. But your injector, then it goes to the guard column. Guard column is supposed to protect the, yeah, and you're right, column, but there's a better word to put before it. Maybe it's business terms again. It starts with an A, analytical column. Probably because they're so super expensive and they're so specially made, right? So the guard column serves to protect it. How does it protect it? What does it do? Does anybody know? Andy's going to play with the HPLC, and he's going to inject, I don't know, some soda water or something, figure out the caffeine and Pepsi or something, right? And he didn't filter what you're supposed to do is you're supposed to suck up this whatever you're going to sample, right? Jam a little filter on there. There's a lot of different ways to filter your sample. This is probably the easiest and the cheapest way because you can throw it all away when you're done. And then push it down really hard. It's kind of hard to push it through. It's a 50 micron filter. And then you just catch what you want, and then you inject it. Well, let's say we didn't have all these, or Andy forgot, so he injects his sample, and no one's going to notice. And if there is some particulate matter in there that's on the order of 50 microns or bigger, it's going to clog up this thing over time. So this is like $500-600. So why not have one of these guys, which are like 20 to 50? So it'll clog up this first, and you just pop a new cartridge in. And the cartridge, I think I passed this around, didn't I, in analytical? Right? There's your cartridge. There's your guard column. That's broken. That's what all that powder is. Okay. So, and they call it an analytical column because look at all the specifications on this thing. They talk about these little glass beads that are packing material in there. And they, like, what is it, 500 microns in size or something, and it's all coated with this special organic material, and they tell you what that is. And it's packed perfectly. Somehow they pack it extremely evenly. Okay, so no spaces or anything. So it's better to call it an analytical column, I guess. Okay, then it ends up going to so the column does its job, everything is separated, goes to the detector. A lot of different detectors. Finally, it all ends up in the waste. Okay, but it doesn't have to. You can actually collect this stuff and put it on different instruments. Okay, which is what a lot of folks do, I guess. Okay. So this is what Kevin and I spent pretty much all afternoon on yesterday. So I guess it's worth something because I can use it to show you guys this. A common detector for liquid chromatography is the DAD, which stands for, does anybody know? Diode, Array, Detector. So what is a diode? Could have had a simple example of one. If you take an LED, right, and let's take a red one that shows the red light, okay? And what I can do is I can shine red light on that and actually hook it up to a voltmeter and actually read a little voltage. And it'll only read a little voltage if I shine red light on it. Or you can go the other way. You can apply energy to the red LED and it glows red, okay? But the point is take a whole bunch of those diodes and just line them up. And what they're going to line up is they're not going to line up, red diodes where the red light is and yellow where the yellow. Nah, it's too much trouble. Let's just line up diode like that solar cell. The solar cell. These diodes, because they'll detect anything. So we'll just line them up, right? We don't care what colors absorb what. Just line them up, get a whole bunch of them, cram them in there, and then here's our grading. That's going to separate out Roy G. Biv the exact same way every single time, as long as we don't bump at this guy. He's nice and calibrated. Blue will always be here, red will always be there, yellow will always be there, right? So you have all your colors, and it's reading a signal from each single one of those 1,024 diodes the entire time. So this is constantly watching red. So it's really what it's doing is it's getting an absorbance spectrum all at once, instantaneously. Because your sample is right here. If the sample absorbs some red, well, then this signal is going to go down from what it was. And remember, what is absorbance? How do you get an absorbance signal? We haven't really talked about this. Oh, let's back up. What's transmittance? They say the incident intensity, let's just call it I's. Why not? I's. There's your initial intensity at some wavelength. And then what gets transmitted? I, some wavelength. Which one will be more intense, assuming it absorbs at that wavelength?
The initial.
The initial, right? If it absorbs at that wavelength. If it doesn't absorb, well, they're going to be exactly the same. But if it absorbs at that wavelength, the initial is going to be a little bit bigger. And then you can calculate the transmittance by saying the transmitted all over the incident. And then times 100 if you want percent transmittance, right? That would be transmittance. But I didn't ask about transmittance. I asked about absorbance. Well, absorbance is just the negative log of transmittance. So that's what I say when I say absorbance. You have to actually measure the incident and the transmitted. So in order to do this, you can't put your sample in right away. First, you have to have a reference or the background or whatever, and just let it get some signal. And then you put in your sample. Okay. So
a diode is just like
a diode for us right now, without taking chem, I would just call it a very similar. Did you ever take a close look at a light emitting diode? You almost have to take a close look at it to see what I'm talking about. And then compare it to what a typical light bulb is. Typical light bulb, you've got that little filament going across. They don't even, I mean, you guys are going to be the last generation of people to even see this thing, right? A typical light bulb, because they're gone. They stopped making them even. So that's a typical light bulb. But light emitting diode, yeah, it still has the two wires coming up, but going across isn't a filament. You have a little junction there, a little piece of semiconductor. So there's a real gap there. Electricity can't even flow. At least with a light bulb, you know, you can actually measure resistance and all that stuff because there's a constant connection. You can't do that with an LED. You can't tell whether it's burned out or not. Anyway, if you apply the right energy across here, it will emit that energy that corresponds to the energy gap in the semiconductor, which is chem talk. But it can go the other way. If that light is shown on there, it can actually detect that color. Okay. So that's a long story for a diode. Array of diodes, just a whole big line of them, right? And then how does it work as a detector? Like I said, we'll put in a reference, then you put in your sample. So come on up here and let me show you how this thing works. So come on this side. Everybody go on that side. And let's have Mel push the buttons or somebody. Okay, so first what we want to do is get a reference. So go ahead and we're going to measure the absorbance of all those colored solutions. So first put that guy in. Now notice how one side is kind of rough, the other sides are clear. So you want to grab the rough sides and then, yeah, exactly. See how the light's going to be going through there. Now, we want to measure the background. So this is already kind of telling you the absorbance over wavelength. Notice how it's a flat line? Mm-hmm. So that means this is already reading. I already zeroed it, but you should just do it again. So just click on the light bulb there. Notice how just leave it there first. Okay. Global reference. So that means just setting a reference. So just click on it. Okay, so there's our reference. We're done. Then you can pop it out. Now, before we put in one of these, we'll just do yellow all the way to green. Before we put in one, why does yellow look yellow? Why does the yellow solution look yellow?
It's reflecting yellow light.
It's definitely reflecting yellow light. That's a good one. So we should not see any, should we see a peak where there's yellow? It would if we changed this to transmittance. But this is absorbance. Okay, let's do that first. Put the arrow over the T. Does that say transmittance? I think it does. Transition. Okay, put that on T. Okay. So it's 100% transmittance. Okay, I wasn't planning on doing it. We'll see if it works. Let's put in the yellow and see where this yellow wavelength is. Right? Yeah, I think it's going to make more sense the other way. Well, this is still okay. It's not going to make sense. Let's stick to absorbance talk. So go back to absorbance. So, because it's a little more complicated. Let's re-reference it again. Yep. Okay, so now before we put in the yellow, this is absorbance. So we shouldn't see any peak where yellow is. What were the colors of the spectrum that you see again? What's the name of the guy? Roy G. Biv. So where's the red and where's the violet on this scale?
Well, red's more towards the 800, right?
Yeah, red should be over here,
should be
and violet should be over here, because it's Roy G. Biv. V is going to be the shortest, red the longest, and that's what this wavelength is. So that means red, orange, yellow, green, blue, indigo, violet, right? You're not going to see much down here. You probably won't see much over here because your eyesight's done. But if we put in yellow, we're not going to, you're right, it reflects the color yellow. And then when you start thinking about absorbance, it's really that it reflects all colors, but it's complementary color. And that's why this solution looks yellow. It's absorbing a region of the electromagnetic spectrum. It's absorbing a region of Roy G. Biv. If you remove this region, these colors in Roy G. Biv, it's going to look yellow. What region is it removing? Does anybody know? What's the complementary color of yellow? Oh, okay. Well, let's try it. So what we're going to do is we're going to put yellow in there, and you're going to see a peak somewhere in here. Now, where the peak is, before you do it though, but where the peak is, that's showing absorbance. That's showing it's being removed. All right, so go ahead and put it in there. So this is in the what region? Bluish. It's a bluish. Because as far down as you can see is about 400. As high as you can see is around 700. So here's red. This is really the blue, deep blue. Okay. So take that one out. How about blue? What's the complementary color of blue?
Yellow.
She says yellow.
Reddish.
Red.
It's like orange, yeah.
Orange. All right, try it.
Wait, the ground's orange. That's orange.
Yeah, it's
Orange, yellow.
Yeah, that's right.
I think this is yellow. Because red's deeper over here. Because Roy G. Biv, red's the last color you can see. The last color you can see is around 700 to 800, depending on how good your eyes are. So this is really yellow. So that's where yellow's at. How about red?
Violet.
Mm-mm. Because remember, you take out the bluish stuff, you get, what did we say? Yellow. We're almost done. You take out the, go back and put this guy in, the yellow. That's blue. So now the red, it's green. It's green. That's where green is.
So then why does it have it like this little peak over here too?
So it's also absorbing something really deep down here that you can't even see. It's getting into ultraviolet.
We should do some pecan. Why don't we
So green would be blue?
What do you think?
do red?
Red?
G.
It's nothing.
No, there's two.
Red and
Green.
blue?
No,
Green?
that's like
That's
yellow.
Remember, yellow was at 500.
Orange.
Yeah, maybe.
Orange and
Orangish
Blue?
kind of. And it's not a very deep, yeah, it's,
This whole thing is new.
We should do
Yep.
some PK today.
you just did it. This is too simple for PK.
Oh.
Taking cuvettes in and out.
Yes?
Yeah.
Need a
Trying to
break?
guess complementary colors. I'm trying to use my.
All right, so have a good day.
I know, I was like, where's the colors of circles?
You saw Federer lost last night?
You did?
Third round against some Italian, I think.
Was he supposed to win the whole thing?
It's the Australian. He lost in the third round, so
Wow.
pretty bad, right?
I guess so.
Have a good weekend,
All
Dr.
right,
Soul.
have a good weekend. You guys can come in now. Hi.
You see the sign that was in the elevator?
Sorry, Kevin. Oh, I'm going to let you in there. Gotta let you into my office there. Yeah, there's some. Well, I used our Spec 20 as a demonstration. It worked pretty good. Yeah,
There you go.
they really liked it. All right, gotta get keys. Yeah.